All right, such a fun and exciting day. First we got chapter 4, now we're getting chapter 5. All right, so chapter 5, we're going to be looking at discrete probability distributions. All right, so if you remember, when we were looking at quantitative data, there was two types of quantitative data. There was discrete quantitative data and there was continuous quantitative data. In this particular section, we want to now talk about the differences between those two data sets, or those two different data values between between discrete and continuous, and we want to find out some of those probabilities associated with those types of variables. So we want to really quickly start talking about a random variable. A random variable X is a numerical measure of the outcome of a probability experiment. So its value is determined by chance. Now remember, a discrete random variable is something that you can count. All right, this was something that was countable. And in a continuous random variable, this had infinitely many values. In other words, they were uncountable. All right, so between these two, we now have to then talk about when is our variable going to be a discrete variable, when is it going to be a continuous variable, because this is definitely going to separate what type of approach we then take for each example. All right, so in the following examples, we want to identify the random variable and sample space. So if we toss a coin for heads, we want to think about what would this random variable look like. All right, so we're observing how many times it lands on heads. In other words, the X, or the random variable, is the number of times the coin lands on heads. Now, the sample space. For the sample space, if it doesn't land on heads, then we get a 0. If it does land on heads, then we get a 1. All right, we start annotating all of this. If we get a 1, that means, hey, we were actually looking at heads because that is something that we wanted to observe here. If we get a 0, then that means, hey, we got tails. Now, looking at part B, an experiment that measures the time between arrivals of cars at a drive-thru. So capital T here, in other words, the event for T. This random variable, we're going to be looking at time between car arrivals. So anything between car arrivals. Now, in this particular case, or any time between car arrivals, in this particular case, time, whether it be seconds, minutes, anything like that, time is just going to be anything greater than 0. So notice, when we're looking at part A, in part A we actually have a discrete random variable because we can count all those heads. And over here, all we're looking at is that the interval is going to be some continuous form of this variable. Whoa, that was rather interesting. Here we go. Continuous. There we go. Now, looking at the definition for a probability distribution. A probability distribution, as you can see the definitions here, but it's just going to be a way to organize the data. My process here, or my thought here, is that you can actually recall these. These are your relative frequency distributions. And this was from chapter 2. So all of these guys, or all of these probability distributions, we've already seen before because we used to know them as relative frequency distributions. We made them in chapter 2 and we made them in chapter 3, which means, hey, they should be familiar to us. Now, the requirements, according to chapter 4, the requirements are that all of the probabilities must add to 1, and each individual probability must be between 0 and 1. So In the following example, when we're given all these three tables, we then have to check, does it satisfy both requirements? In order for a probability distribution to be valid, it must satisfy both. If it does not satisfy one, then we cannot use it as a probability distribution. So I want you to take some time really quickly and just to investigate part A, B, C. Do all the probabilities add up to 1? And is each individual probability in between 0 and 1? So take some time and review that for yourself. All right, so now that you've taken some time, let's go ahead and let's start discussing. Look at all the probabilities in part A. All of these probabilities, they all satisfy the first requirement that they're all, second requirement that they're all between 0 and 1. However, when you take the sum of those probabilities, we get 0.97, which is not 1, which means it's not satisfied. All right, so which means at this point in time, we can say, hey, this is not equal to 1. And that's all we have to say if we want to justify. Part B. Well, looking at part B, in part B, we can see that if we add them all together, the sum will be equal to 1. So the probability of all of these added together is 1. However, this probability does not meet this requirement because it's negative. It falls outside of the interval, which means, hey, this probability is no good. Probability distribution. The last probability distribution, part C, is the one that's going to work. Part C is going to be the one that meets all of the requirements that each individual probability is between 0 and 1, and all of the probabilities added together gets us a value of 1. Very nice. Now, for the next question, we want to answer this, that a couple plans to have 4 children. 4 children. Let X be the number of boys the couple will have. So we want to find the probability distribution for the number of boys. All right. So find the probability distribution for the number of boys. All right, let's see if we can go through that. Now, bear with me. This is going to get somewhat intense. Yep, somewhat intense. All right, so here we go. All right, I said here we go and then I didn't go, but it's okay. So I'm going to take this space right here, this blank space, and it's not a big blank space for me to work on. So what I'm going to do is I'm going to come down here and I'm actually going to show you down here what it is that we're looking at. What I'm going to do here is I'm going to draw a tree diagram. So this is a tree diagram, and we use this for statistics every now and then. So what I want to do is I want to look at what are the different outcomes when I'm looking at having boys or girls. So for this tree diagram, I'm going to be looking at outcomes, boys and girls. All right. So for the first outcome, when this couple wants to have a baby, what are the 2 outcomes? Well, naturally, the 2 outcomes that we're going to have is going to be either that the baby is a girl or the baby is a boy. All right, so this is the first outcome. All right, first outcome, or first child. Now we need a second child. For the second child, what are the possibilities again? Well, the possibilities again are going to be either the baby was a girl or the baby was a boy. Same thing down here. If the first child was a boy, then for the second child, they still have the same options. They could have a girl or they could have a boy. So that's the possibilities for the second child. Now we're going to look at the possibilities for the third child. The possibilities for the third child. If they had a girl for the second child and a girl for the first child, then naturally they're still going to have those exact same options. You're going to have a girl or a boy. Same thing here. They can have a girl or a boy. Same thing here. They can have a girl or a boy. And same thing here. They can have a girl or a boy. And for the last outcome, the fourth child. Whew, I know this is tough. It's okay, bear with me, bear with me. There's going to be an easier way to do this, but we have to get our legs dirty for now. All right, so here we go. Fourth child. I don't like the way that looks. I did not guarantee it. That's a Men's Warehouse joke for anybody that didn't get that. All right, here we go. Fourth child, they could have a girl, or they could have a boy. They can have a girl, or they can have a boy. They can have a girl. They can have a boy. They can have a girl. They can have a boy. Again, they can have a girl. They can have a boy. Again, girl, boy. Again, girl, boy. And again, girl, boy. Whew, I know. Really, really tough. Now, let's start analyzing all of this as to how or what are all of these different combinations. So all of these different combinations, what we want to do is, we call this a tree diagram because it looks like it has trees with branches. And what we want to do is we just want to go down one of the branches, looking at one of the possibilities. This possibility was a girl, this other one was a girl, this other one was a girl, and this other one was a girl. In other words, one of the possibilities is that this couple has all four girls. Well, let's look at a different possibility. First possibility was that they could have been a girl. Second possibility, girl again. Third possibility, girl again. But this time the fourth possibility could be that the baby was a boy. Nice. All right, let's go down another branch. So we already got this branch, we already got this branch. Let's go down the third branch, fourth child down. So that's girl, girl, this time boy, and then girl. So that's girl, girl, boy, girl. Nice, that was the third branch. Let's look at the fourth branch. Fourth branch, so girl, girl, boy, boy. So girl, girl, boy, boy. And we're going to keep going. All right, so that was that fourth branch. Let's keep going. So now girl, boy, girl, girl. So girl, boy, girl, girl. The next one, girl, boy, girl, boy. That was this one. So those two are done. So far, 1, 2, 3, 4, 5, 6. Let's go with the next one. We can have a girl, boy, boy, and then a girl. That was following this branch here. Nice. Next one is that they could have a girl, boy, boy, boy. That was this possibility here. The next one is, wow, now we're done with all the girls being the first child. Now the boys are going to be the first child. So boys being the first child, we're going to go through the same process again. So I'm going to start a new column here. All right, starting a new column here. So it's going to be boys. That's according to this one. Then we go to girls. Then it's a girl for the third child. And then it's a girl for the fourth child. So boy, girl, girl, girl. Next one, boy, girl, girl, boy. So that was boy, girl, girl, boy. The next one, boy, girl, boy, girl. The next one, boy, girl, boy, boy. Good. So that's these two done. The next one's going to be boy, boy, girl, girl. Next one is boy, boy, girl, boy. The next one is boy, 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 girl. And the last one is that all four kids are boys. Now, in total, there should be 16 probabilities, or sorry, 16 outcomes. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. A total of 8 possibilities. Wow. Sorry, 16 possibilities. Wow. Interesting. So I'm going to take this and I'm actually going to use this on the top part. Now I'm going to try a new feature here. Let's say that I lasso this around here and see if I can copy and paste some way, somehow. Bear with me here. Boom, look at that. Oh my gosh. Let's cut this. Oh, it's working. Now here comes the big reveal. Will it paste? All right. Let's see. I don't know what that button does. Nope, that button does copy, but I cut everything, so let's see. Whoa, whoa, whoa. ¿Qué pasó? Yes, yes. Let's go to paste. Whoa, there it is. Okay. Okay. Let's undo that, and let's actually bring it over here. I want it right here. So can you paste this right here? Let's see. Touch that there, and ooh, nope. Let's move it here. There we go. All right, let's paste. Nope. Wow. Oh, you know what? My apologies. My sincere apologies, everybody. This doesn't seem to be working with me too well. You know what? And that's okay. That's okay, because at the end of the day, we kind of see what's going on here. So I'm going to leave this down here. You know what? I'm going to play around with this program. Hopefully make this a little bit more smoother as we keep going through the course. So let's start looking at this. We're going to start filling in the table that we had up top right over here. So we want to fill in this table where we have X is the number of boys the couple will have, and we need to find that probability. So let's look at the probability of that couple having no boys. So the probability of that couple having no boys, see if we could find that. No boys. Which outcome has no boys? That should be the first outcome. All right. So that's 1 out of how many? That's right, 16. So in here, whoa, that was 155. There we are. All right, so in here, we get 1 out of 16. Great. Now, how many of those outcomes only had one boy as a scenario? Only one boy. Count them up. 4 out of 16. How many had 2 boys? 6 out of 16. 3 boys. 4 out of 16. 4 boys. That's only one scenario. There we are. Now we can look at the probabilities in decimal form if we'd like. All right, this is 0.06. Sorry. 0.0625. Next probability 0.25. Next probability 0.375. Next probability 0.25 once again, and next probability 0.0625. There we are. So 16 different ways to have kids, but then these probabilities are within those 4 children. What's the probability that they will have this number of boys? So we have this listed. Very, very small chance of them having 1 boy, but look at this. It's a rather high of a chance for them to have 2 boys. In other words, for them to be half of them. And it's not exactly 50%, as you see here. It's like 37.5%. Which is really nuts because, again, the more kids that you start having at this point in time, it's not exactly 50-50, which is really interesting. All right, so we kind of want to keep that in the back of our minds. Now, looking at some of these formulas, again, when you take an exam, you will have these formulas. Now, unfortunately for us, since we're no longer in class, in a classroom setting, those formulas are going to be accessible to you guys on the computer or through Canvas. All right, so you still will be able to use these. So we want to go through and we want to use these formulas to answer this question here. that says, in a study of brand recognition, random groups of 4 people are interviewed. Let X be the number of people who recognize Jeff Bezos when shown a picture. The following probability distribution gives the likelihood of a random variable. All right, so the question is, who the heck's Jeff Bezos? Now, for all of you that don't know, he's Amazon CEO. All right, so we want to see whether these people that were shown the picture of him are gonna recognize him. So X is the number of people who recognize Jeff Bezos. So in this group, nobody recognized him. That was a probability of 0.01. In this group, only one person recognized him. That was a 0.10 probability. That 2 people recognized him. That was 0.24. That 3 people within the group recognized him. That was 30%. And within the group that 4 people recognized him, that was 0.35%. So we want to identify, is this a probability distribution? Is this valid? So is this valid? Yes, it's going to be valid. It's going to add up to 1, and every single probability is between 0 and 1. So what we want to do next is we want to start filling in this chart, this table that we have here. So we're going to take our variable, our random variable, and we're going to multiply it by the corresponding probability. So in other words, you're going to multiply 0 times 0.01. We get 0. 1 times 0.10, we're going to get 0.10. 2 times 0.24, we're going to get 0.48. 3 times 0.3, we're going to get 0.9. And then finally 4 times 0.35, we're going to get 1.4. Nice. All right. So what we're going to do at this point in time is we're going to add all of these probabilities, all of these products. And the reason we're going to add all of these products is because this right here, sigma, is going to tell me that I need to add all of these products together. So let's add them all together. We should get somewhere along the lines of 2.88. Now what we're going to do for the next one. For the next one, we're going to take x squared and we're going to multiply it by x. Now it's kind of similar to what we did before when we were looking at finding the mean of a the mean of a frequency distribution. And if you go back to chapter 3, we kind of see that the mean of a frequency distribution, mu, is still going to be the same as the one that it is here, the one that's given here. All right. The notation is slightly different, but again, it's still the exact same process that we're working with. So instead of, the reason I say this is because instead of finding x squared times p of x, I gave you all a nice little trick to say you take this column, and we're going to multiply this column by x. In other words, by this column. So we multiply these two. Multiply, and that's going to get us the third column. All right, so let's multiply. 0 times 0 still gets us 0. 1 times 0.10 still gets us 0.10. 2 times 0.48 should get us 0.96. Then we're going to take 3 multiplied by 0.9. That's going to get us 2.7. And then we're going to take 4 and multiply by 1.4. And we should get 5.6. Finally, we take sigma of all this. In other words, we add to get 9.36. Nice. So in order to fill this table in, we had to go through a little bit of algebra work. Not too bad, but now we have to answer the questions. So part A says, what is the probability that more than 2 people will recognize a picture of Jeff Bezos? So the probability of more than 2 people. Now I'm going to erase some of this here. All right, probability of more than 2 people. Let's see. More than 2. So more than 2, strictly more than 2. Does that mean probability of 3? Yes. Probability of 4? You betcha. So here, more than 2 means that we take the probability of 3 plus a probability of 4. But those probabilities, probability of 3 was 0.3, probability of 4 was 0.35, which means this probability is 0.65. Or we can say 65%. Not too bad, not too bad. All right, next one. Whoa. Cheese and crackers, man. All right, here we go. Technical difficulties, but you all know me. I have technical difficulties anywhere that I'm at. So, question B, what is the probability that at most 3 people will recognize Jeff Bezos? So, at most 3 people. So, let's see. At most 3 people. All right, so I'm going to go back to my chart over here. At most 3. What does at most 3 mean for us? At most 3, meaning that it could have been that 3 people identified him, but that's at most. That's most people that would have identified him, which means 2 people could have identified him, 1 person, or no persons. In other words, would you agree that at most 3 is just all of the probabilities added except the probability when x is 4? Because that's going to include 0, 1, 2, and 3. That's going to include all of these probabilities here, except this one. That's the only one we don't need. Which means this is just 1 minus 0.35. And what do you guys get there? 0.65. Nice. All right. Now, finding the mean. So let's go ahead and let's find the mean of this probability distribution. And if you notice, what I'm doing right now is I'm scrolling just a little bit up, because what I want to do is I want to look at the mean of the probability distribution. The mean of the probability distribution just means that we add all the random variables multiplied with their corresponding probabilities. That sum we already have. That sum is on column 3. Column 3 says that the mean should be 2.88. Nice. What about standard deviation? Look at that formula here for standard deviation. Standard deviation here, so we're going to go ahead and we're going to calculate that standard deviation. Standard deviation here, we're going to take the square root. Now we need the summation of all the x squareds multiplied by the corresponding probabilities. That's the sum of the last column. That's 9.36. And we're going to subtract out the mean squared. This is what we want to see. So now that we have that, let's go ahead and let's insert this into our calculator. So I'm going to access the square root. Square root is right here above the x squared figure. It's in blue, so I'm going to hit second square root. There we are. And then I'm going to type in 9.36 minus, I'm going to open my parenthesis and I'm going to type in 2.88. Close that parenthesis, square that. There we are. And I'm just going to hit enter. I get my standard deviation. Standard deviation is 1.032. Very, very nice. All right, so this probability was approximately 1.032. Awesome. Oh, sorry, not probability. This standard deviation. Nice. All right, so that's how we're working with probability with these probability distributions, how to find their mean and how to find their standard deviations. Now, an important result from this is that we can now start talking about expected value. Looking at expected value, we're going to denote this expected value as E, capital E. This expected value is, or the expected value of a discrete random variable represents the mean value of the outcomes. In other words, on average, what should be occurring. All right, so on average, what should be occurring? So let's go ahead and take some time and let's read this first example. All right, so here we go. There's a game in Vegas where you pay $1 to play. The possibility to win either $5 or $10. Now, this is going to mean that we get a net payout of $4 or $9 because, again, we paid $1 to play. So the probability of a payout is $4. That's with a probability of 0.3. A probability of a payout of $9 with probability of 0.1. find the expected value for this game. In other words, if we play this game long enough, what should we expect to see as our income? All right, so let's see. X. Well, what are the possibilities here? So we want to look at possibilities. In other words, outcomes. Could we win $1? Yes. Could we win $4? Yes. Or could we win $9? All right, that's a big question. All right, here we go. So we're looking at these outcomes where we can play $1, win $4, win $9. But when we play $1, that means that we're going to be losing that $1. So we naturally denote that as a negative because it'll be a loss. Probability-wise, all right, probability that we get or that we win $4, that's going to be 0.03 according to what we have here. So that's going to be $4, 0.03. And then a probability of 0.01 or 0.1 to win $9. All right, so that's going to be 0.1. And then whatever remains should be the complement. If we didn't get the $4, if we didn't get the $9, if we didn't win those, then we must have lost. And that probability should just be the complement, which is 0.6. Now, we then need to find what is this expected value. So in order to figure out what this expected value is, we need to figure out what the product is of these two. In other words, we need to figure out what their multiplication is. So x times p of x. So multiplying this is going to be 1 times 0.6. That's going to be negative 0.6. We're going to multiply 4 times 0.3. That's going to be 1.2. We're going to multiply 9 times 0.1. That's going to be 0.9. We're going to add this up. So to find the summation here. So adding all these together, we get 1.2 plus 0.9 minus 0.6. We should get around 1.5. And that's positive. That means that if we play this game many times, we should expect, on average, a win of $1.50. Now, this doesn't guarantee that we win, and again, it doesn't mean that we will get it. It just means that if we play this long enough, we will be netting some positive income. All right. Now, this is important because if you start dissecting all of the expected values for every single game that they offer in Las Vegas, yeah, all those expected values are going to be negative, which means over time, the house always wins because the expected value for the player will always be negative. All right. So let's look at this expected value when we're looking at it from an insurance standpoint or from an insurance point of view. So when someone buys life insurance, the policy will pay out a sum of money to what we call a benefactor upon the death of the policyholder. So suppose a 25-year-old male buys $150,000 life insurance for a 1-year term, and he's only going to pay $250 for it. The probability that the male will not survive the year is 0.0013. So the experiment has two possible outcomes. That means that they either survive or they die. Wow, I know it's kind of morbid. Here we go. Let the random variable x represent the money lost or gained by the life insurance company for the 25-year-old male after many years. What is the expected value for the company? All right, so I'm going to start this the exact same way that we were doing before. I need to look at some scenarios here. So I have x, I have p of x. I'm also going to need x times p of x. All right, so what are those outcomes? Well, the person either survives. Oops. Wow, that is not how you spell survive. That's okay, though. Survive or dies. All right. Let's see. So again, this is from the standpoint of the company. If the person survives, if the 25-year-old male survives, that insurance company will make money because they don't have to pay out. Which means if the individual survives, the company will make $250 out of this. However, if the individual does not survive, in other words, the individual dies, then we're going to take the $150,000 and we're going to subtract out the $250. And this is how much the insurance company will have to pay out. $149,750. So that's how much money the insurance company has to pay out if this individual dies. But since they're going to pay it out, that means it's going to be at a loss for them. So negative $149,700. That's going to be the loss for this insurance company. Now back to the probabilities. What's the probability that the male does not survive? So that the male not survives, that probability is 0.0013, and that was given right above. Now we're going to use a complement of that. The complement means that the male should have survived. The complement of that means that we just do 1 minus that probability. So I'm going to do that on the side over here. So it's going to be 1 minus 0.0013. And this should get us a probability of 0.9987. And that's a probability here, 0.09987. All right. Then we multiply across like we typically do. So this is going to be 249.675. 0.675, and the other one's going to be negative 194.675. So to find the average, or to find the expected value, all we do is we add these. So add those two. Now when we add the two, we should get an expected value of $55. This means that the insurance company will make, on average, $55 for each of these policies. So, and again, this is on average. So as long as they keep selling these insurance policies, they're going to be making $55 for each of these individual policies. All right. So again, they stand to make the profit. Now, the next, or the sub part to this, says that over 1,000 policies, how much should they expect to make? So now if they're selling 1,000 of these policies, well, let's look at this. Since we got an expected value of $55, we expect to get $55 for each policy that they sell on average. And again, they're going to sell 1,000 of these, which means 1,000 times 55, they should stand to make $55,000 if they sell 1,000 policies. That is insane. That is, again, what we're looking at here. So I want you to take some time, and I want you to read through the next example and try to see if you can set this up for the next example. All right. Now, I am going to give you the answer to this, but I'm not going to give you the answer to this just yet. So I'm going to have you wait on this a little bit longer in order for me to give you that answer. And I'll give you the answer at, let's say, the start of the next video. All right, so stay tuned, people. Stay tuned.